continue with John Snow's experiment. So in this map is the bigger region for the London area. In this area, basically their living environment are very similar. So they only have one difference for those households is their water source. So that's why we break into two groups. The first one is the treatment group. The other one is the control group. Usually the control group, we say they do not receive the treatment. And the treatment in this case is the water source from S and V. It's very important for the treatment group and control group. They basically are identical. The different thing is the control group didn't get the treatment. So on the other hand, when we want to get our comparison, there is no difference whatever in the houses or the people receive the supply of the two water company or in any of the physical condition with which they are surrounded. So that's why the Snow's grand experiment can have these two groups. In our experiment, that's very important. These two groups actually should be randomized. On the other hand, this randomized make them kind of no difference. The only difference is the treatment group received the treatment. So that's why in this map area, the surrounding environment, they are very similar. The only thing is the water resource is different. So from here, actually, John Snow got the table here. This one, actually, we have the three columns. The first column is the water resource from the SMV. Then the second one is from the land bath. Then we have the rest of the London area. So I want you to observe the data here and see what you found. The first row is the number of the household in different regions. Then the second one is collateral death number. So then we also have the death number for per 10,000 household. If necessary, you can pause the video and see what you found. I believe many of your conclusion, you will say, yeah, the SMV actually have much more collateral death than the land bath. But one thing we also need to be careful. The SMV actually serve more houses as well. That's the reason we divide the deaths by per 10,000 households. So that's why we can see by every 10,000 houses how many deaths. Then you can see the SMV actually is much more than land bath, and also even much more than the rest of the London. This is a very good example for the Snow's experiment. To have the two groups, the experiment group and control group, basically they are very similar, except one thing, the treatment. The important thing to establish causality is the treatment and the control group, they are similar from the treatment. And on the other hand, in the statistic, we call that the randomized data. So the randomized data, we are systematically to get a group of sample. So then when we break that into two groups, like here, we got 500 students, college students. So then we try to make them into two groups. We call that control group and the treatment group. We just random break them into the two groups. We cannot like say, oh, we have the female and the male apart, or we have the age different. So when you have anything kind of add one restriction to break the two group, they are not randomized. Okay, even they came from the same selection for the sample data. So that's very important key when we establishing the causation. Our treatment group and control group, they are random selected and they are very similar. Then when we break them into two groups, we only have the treatment make them has difference. So that's why we back to earlier our heart disease example. If we want to make them have establishing the causality, we need to also make sure we have to go back to see when they select the adult, we need to know they are got the random data for that. Okay, so that's the key to establish the causality. Otherwise, we will have the confounding happen. So what is confounding? If the treatment and the control group have systematic differences other than the treatment, then it might be difficult to identify causality. Such differences are often present in observational study. When we lead research trait, they call confounding factor. So you can very easily to see, because earlier, for example, our water resource data, like we told you, in this area, all the houses, they are in very similar environment. Okay, so one thing is when we say they only have the water resource different, they only can be this treatment is different. So on the other hand, you can see if the way how they build their housing material, or the electronic resource, or some other thing, maybe their food or something, if they have quite differences, then we cannot have the conclusion here for the table to observe from. So that's very important when we have our treatment group and the control group. They only have one thing different. Otherwise, you can see here we have a couple examples for the confounding. So these two, we have a couple diagram we want to show you. You can see these two lines actually they have very similar traits. But one thing is, the first one, the red one, is the divorce rate in men. Then the black one is the consumption of migrant. So then we cannot say because they have very similar traits, then this one actually the consumption of margarine is the treatment. So that means your consumption of the margarine will cause your divorce rate in men. So that's the outcome. So we cannot say that, right? Because they have many different, we don't know how the data came from. And also except the consumption of the margarine, they may have other things they are different from the data. Then the other thing is, here is the cheese consumption is in red. Okay, so then the number of people who died by becoming tangled in their bed sheet. Even they have very similar pattern for their change of the data. But then we cannot have those data we say they have direct result. So the treatment not really cause with the outcome. So even have the other funny one is this one. So you can see even they are not very similar trend for these two data. Okay, but one thing they have something very similar, like especially after the 2000 and also before the 2000, these two lines they kind of in the same pattern to go. So the funny thing is this one is the film Nicolas Cage appeared in, and the number of people drowned by falling into the pool. So we cannot really give them the conclusion is because we don't know those data. The treatment is not the only thing separate the data group. So when we do our experiment, very important is randomize. When you assign individual to treatment and the control group at random, then the two groups are likely to be similar apart from the treatment. And also the other thing we want to talk about is, even like earlier we say, for now, maybe I random select 500 students from DVC. Okay, no matter they are female, male, or their height and weight, we just random got 500 students DVC. So then we just make them randomly break them into two groups. One is treatment group, one is control group. So the treatment group may be like we say we want them to eat 10 chocolate bars every day in 2 months. So the other one is not. So then we can do the result to observe our result 2 months later. So even earlier we told you you have the two treatment and control group we get from random. But when we start with the study, we cannot let the student know they are in treatment group or control group. So that we call that the blind experiment. Because if you let the treatment group or control group people know which group they are, they may affect their emotion or feeling or something. So when we do the mathematically research or analysis, when we assign the individual and treatment group, control group at random, we need to make sure we have the blind experiment. So that we call the randomized control experiment. So this one actually is another example you can see from here. Okay, so this one is we call the control group and the treatment group. So the blue line is when we have the Pfizer shot. So the other the red line actually is the placebo shot. That means we give them the shot, but actually it's just it's not a Pfizer injection. So these two lines you can see after, especially we say the second shot given by after the 21 day. You can see this one actually is the accumulative incident of the COVID. We know that we have the COVID vaccine. We are not prevent you to get the COVID. You still have possibility to get the COVID. But you can see this line, their rate actually, if you have the vaccine, they are kind of very unstable. It's no change. But without the vaccine, so then you can see during the dates goes by, their accumulative chance, not the chance they got the COVID times, actually they go going on by the times. So that's the same thing we call the control the treatment group and the control group. When you have these two treatment group and control group, they may know what they are doing, but they cannot, when they take the shot, they don't know they got the Pfizer shot or not. Okay, so that's what we call that the blind experiment. And one thing is we need to be careful. The randomized is not really equal to the hypothesized. When we do the randomized in statistics, actually systematically to apply the data. So even the dictionary have the same explanation. We need to be careful about that. Okay, so then it's just the comic to talk about the association and the causation. So I hope after this lecture, you have better understanding. So don't forget, after lecture 2, so you have your homework assignment. The same thing, access the link for the homework assignment to complete your assignment 1 and download